Identify the dependent and independent variables in the following situations. That's what we did 2 times ago. Determine whether the situations are linear or nonlinear, which is pretty easy on a graph. For the situations that are linear, construct a function that models the relationship, which we will do in the form y equals mx plus a b, but instead of y, we'll just put f of x. An object is dropped from a bridge into the water below. The graph below shows the height of an object in foots with respect to time in seconds. Consider the relationship between the height of the object and time. Well, x is always the independent variable, so that would have to be time right here. I'll put in time for these. The dependent variable is the y, so that would be the height. Is the data linear? Well, linear indicates that it would be a straight line. This line is extremely straight and never is straight because it's curvy, so it's not straight.
So that's non-homework then.
So this is nonlinear. Well, since it is not linear, then we will not need to construct a function for it. Owen is earning pennies each day that he makes his bed in the mornings. On the first day, Owen's mom give him 2 pennies. On the second day, Owen's mom give him 4 pennies. Third day, 6 pennies. Fourth day, 8 pennies, and so on. Owen makes his bed every day, and this pattern continues. The model below shows how many pennies Owen earns each day. Each box represents 1 penny. Consider the relationship between the number of pennies given on a given day and the day number. So this one is not graphed for us, but it has given us a model, which is a very nice model. And we should be able to identify the independent and dependent variables. It seems on this one that the number of pennies he receives will depend. So the pennies depend. We'll put that in here, pennies. Will depend on the day. There we go. And is this one linear? Well, we could graph it if we wanted to, but we can see that each day we're adding 2 pennies, adding 2 pennies, adding 2 pennies, which indicates that there is a constant rate of change. So this one is linear. And for these, we got y equals mx plus a b. So b being the y-intercept, how many pennies did Owen start with? 0, right? He received 0 pennies on day 0. So that would be plus 0 right here. But what is the sloppage? Well, we can see that there's an increase of 2 pennies every 1 day. Now, of course, we don't have to write it as 2 over 1. We could write it as just 2. And since it wants this to be a function, we can replace the y with a good old f of x. This is just a continuation of what was going on up in here. And we can just look at the day numbers that we can put on here. 1, 2, 3, 4, 5. And the number of pennies added that day, well, 0. Didn't really add any pennies. Well, I guess they did. We added 2 pennies that first day, 2 pennies the second day, 2 the third, 2, and then 2. So the sum of the pennies then becomes, on day 1, they will start with 2 pennies, and then on day 2, then he got 4 more pennies, so he actually had 6. And then on the next day, he got 2 more pennies, so that would have been 6 plus the 6 that he had, so that's a 12, right? And then the 4th day, he got the 12, but then plus 2, 4, 6, 8. So that's 20 pennies right here. And then the 20 plus 2, 4, 6, 8, 10, 30.
I was at the start of that, I was like, I know where you're going. And then you said,
So remember, he's getting more pennies every day, right?
Yeah.
So the first day, he's getting 2 pennies. And then the second day, he gets 4. So the sum of the pennies would be 6. So he's got 6 pennies, and then his mom gives him 6 more for the next day, 12 pennies total. Right. So this is how much he has every day. Well, from this, we should again have the same independent and dependents. We got the days. And the dependent is, well, I guess it would be the sum of the
Wait,
pennies
so
in
that
this
means,
case.
wouldn't the second column be wrong then? Because it'd be +2 and then +4 and then +6 and then +.
Yeah, I guess it depends on how you want to write that stuff. So we're just adding 2 every day and, yeah, 4. That would have been a lot easier to refer back to it, yeah.
But you're not adding 2 every day, you're adding.
I mean, just out of curiosity, if we're looking at day 6, how many pennies would he have?
60.
Oh, wait, it makes sense.
Close.
I
42.
can't count that much.
Because he had 10 from the 5th day, so add another 12. Bam, so
Can I
42.
count to that number?
So is this linear though? Well, we got to look at these just in terms of one table. And we don't need to go very far to determine this. We got the days and the number of pennies. 1, 2, 3, 4. That's how many pennies he had. 2, 6, 12, 20. Now, in order for a table like this to be linear, it's got to have a constant rate of change. So right here, we added 4 pennies for 1 day. Now we're going to add 6 pennies for 1 day. So that already shows an inconsistency in the number of pennies added. So this one is not linear.
Oh, I see what you're doing now. I just thought in my head a little bit. I was like,
It's not linear because there's not a constant rate of change.
So would number 2 be not linear then?
Hold on, not a constant rate of change. There we go. The difference between this one and the last one that we did was that we were just looking at how many pennies were added every day. Well, hold on. So we're looking at how many pennies he was getting every day. This one's looking at how many pennies he has after every day. All right, and this one was not linear, so we don't have to worry about creating a function. However, in 9th grade, you will, and you're going to love it. Carbon-14 has a half-life of 5,730 years. The table below shows the amount of carbon-14 that will remain after a given number of years. Consider the relationship between number of years and amount of carbon-14 remaining. Now, this is all common knowledge, so you guys should know this already. But we can identify the dependent and independent variables. And, of course, how many milligrams of carbon-14 will depend on how many years have passed. So we got milligrams of carbon, so it's just carbon is C, I think. Frankly, I don't even care. Carbon-14. And the independent then will be the time in years. So is this linear? Again, we got to look at the table. And we are just looking for a constant rate of change. So between this first set, we have a change of 4, it went down 4 milligrams in 5,730 years. That was added. Well, what about the next set? Well, that went down 2 milligrams for 5,730 years. Well, that also, again, shows an inconsistency because one took 5,730 years to take off 4 milligrams. Then the next time, 5,730 years happened, it took 2 milligrams. That's different. So automatically we can see that this one is not linear because, once again, there's not a constant rate of change. Of course, that's a lot easier to see in a table. I'm sorry, not a table, a graph. It's a lot easier to see in a graph because it would show some kind of curviness. And since this one was not linear, we do not need a constructive function for these. Steve is a lifeguard at the local community pool. Each day at noon he records the temperature and the number of people in the pool. Do you think the relationship between temperature and number of people in the pool is linear? This one depends, really. It depends, because on a graph, that's what we talked about last time. So linearity will create a straight line on a graph like these. So the people at the pool, this would be the number of people. will depend on the
Does that mean a
temperature.
straight line, and then that means it is.
Well,
Can we draw this cross?
yeah, I'd assume if the temperature is 0, you'd get 0 people there. But as the temperature rises, for example, if the temperature were a little bit more than 0 degrees, it'd probably still be 0. However, the problem with that is that it's probably not open if the temperature's that cold. So the temperature will only be temperatures which would be convenient for people to be there. So it probably would be pretty linear, something like this. Now we did do scatter plots, so even if the scatter plot created something that the line of best fit would give us something linear, that would be fine as well. And this is something that we would expect to be linear.
Because it's straight.
Now, yeah, if we were saying it was open and temperature 0, probably not, because you'd get a few temperatures with 0, but that's not really what we're talking about here. So, in context, yes, we would expect this to be linear, because as the temperature increases, we would expect the number of people to increase.
At the same
Proportionally.
rate of change. Right?
Put the cyclists in order from slowest to fastest. So that means we're going to have to look at the meters per second, and just the speed of each of these. So for example, this guy increased his distance by 1 meter, but unfortunately it took 2 seconds. So this person's going 1 meter every 2 seconds. That is his rate of change. Cyclist B, it says cycle 12 meters in 6 seconds. That one right there is the reciprocal, 2 meters for 1 second. So we already see that cyclist B is much faster. Cyclist C, this one's in an equation, and that equation tells us the sloppage is 1/3, so 1 meter every 3 seconds. And then finally D, we can look at 2 points. This person went 2 meters in 3 seconds. So their rate was 2 meters in 3 seconds. So it says to list them in order from slowest to fastest. And right here we can see that cycle C is the slowest. And then the next slowest would be cyclist A. And then the next slowest cyclist D. And finally the fastest, cyclist B. Based on the information below, which bathtub will be empty first and why? Well, bathtub A starts with 25 gallon and is draining at 1.5 gallons a minute. So at 1.5 gallons every minute. This one, it appears, will take 20. So we're going to take the 20 gallons and divide it by 1.5 gallons per minute. Oh yeah, 25, thank you. So I'll just take this off right here. 25. So that should give us, 50/3 minutes, which we can convert to about 1 and 16.6 repeating minutes. So that would be bathtub A. Bathtub B also has 25 gallons, but we can see that it drained out 5 gallons in 3 minutes. So 5 gallons every 3 minutes. So again, 25 gallons divided by 5 gallons every 3 minutes. 5 gallons. And then we should get, so this one will take 15 minutes to drain out. And then bathtub C, we can see that this one also starts with 25 gallons. And if we look at the rate, yeah, I got this point right here. So it went down 4 gallons in 3 minutes. So we'll take the 25 gallons and divide it by 4 gallons every 3 minutes. And this one would be, well, I guess 75 fourths minutes, which changes into 1 and 16.25. Minutes. So which one will be empty first? It appears that bathtub B will be empty first. Why? Because it will take 15 minutes.
Oh. We have to write. It's great.
Number 8, 4 families are meeting up in Old Disneyland. Each family start driving from home. The representations below show the distance each family is from Disneyland over time. Assume the families drive to Disneyland at a constant rate. So they've shown us this equation up yonder, and they made that's family A. There's 4 different families, that's right. Family A is represented by the equation. Family B is represented by the wordage. C with the table, and D with the graph. So, based on these 4 things, we got to determine the answers to A through whatever the heck it goes to. And on A, for example, there's a couple things we need to determine is how far do they live from Disneyland? Just looking at that equation. Now we could rewrite it, by the way, as y equals negative 55. What the heck happened there? Negative 55x plus 95, right? So looking at that equation and knowing what we know about equations, not that we remember it all the time, how far away does family A live from Disneyland? Yeah, 95 miles. Very good. And how fast are they traveling? 55 miles per hour. We'll need to remember that. Because family B, it says they live 120 miles from Disneyland, but they drive 60 miles per hour. So who's driving faster, A or B? B so far, and who lives farther? B, okay. So we'll have to determine perhaps which one will get there the fastest. Family C, how far away do they live from Disneyland? How many miles? 80 miles, very good. And what is their rate? What is their speed? How fast are they traveling? Well, right here we can see that they traveled 75 miles in 1.5 hours. I think that is 50 miles per hour. So right now, amongst those 3 families, even though family C lives the closest, they're also going the slowestest. Family D, how far away do they live? Yeah, we'll need to know that. Right there, very good. 45 miles. And how fast are they traveling? Where did I show that? I guess that's 1.1 right here.
40 miles an hour.
That's right. It's got this point right here at 1.5. So we can see that they traveled 40 miles in this 1 hour. Very good. 40 miles per hour for these guys. Living 45 miles away. We don't really need that garbage. Alright, so which family lives the closestest? D does, right? Because they only live 45 miles. Which family lives the farthestest? B, right? Is that what you guys said? Which family is traveling the fastestest? B. Which family is traveling at the slowestest? D, right? Yeah, right. 40 miles per hour is the slowest. Who will get to Disneyland the fastestest?
Now we have to do that.
Yeah, now we got to look at the map, right? Well, in terms of distance, well, let's look. family B, this one's pretty easy. How many hours will it take them to get there? 2 hours, right? How many hours will it take family A to get there? Well, you got 95 miles at 55 miles per hour, so 95 divided by the 55. So this family will take 1.8 hours. Seems like there should be some repeating there. How many hours will it take family C?
1.6.
Is that right? 1.6? Yeah, 1.6 miles, hours rather. And then we can, well, how long did it take family D to get there? Well, 40 miles per hour at 45 miles. So,
Like 1.1.
yeah, it's something like 1.1-ish. So who got there first? Family D, but they were going the slowest though. But they lived so close it didn't matter. Very good. Who'll get to Disneyland last? B? But they were going the fastest. Yeah, they were so far away it didn't matter.
That sounds kind of depressing.
That's what you
For each problem, circle the representation with the greatest rate of change. Put a star by the representation with the greatest y-intercept. Assume all representations have a constant rate of change. So these are all linear. That's nice of them. And right account. Let's look at the rate of change for these. This one, we got these points. Where's the next one? This one. This one has a rate of -7/2. So this one's rate of change is 7 over. I guess they gave it to us in this. Hey, that's okay. What about this one? Well, this one increases by 12 for 4. So that has a rate of change of 3. Right account. This one goes down 6. And then up 2. So this one's rate of change is -3. This one, we got a rate of up 4 to the right 2. So this rate of change is 2. And then down here, we'll use rainbow method. 3 to -5 is -8. And then 0 to 2 is 2. So that's a -4. So the biggest rate of change looks like it is this one. Because negatives are less than positives. Wait, no. Hold on a second. Let's take that back. Yep, 9 has the biggest rate of change because 3.5 is bigger than 3. That's even better. All right, so which one has the biggest, the greatest y-intercept? This one's 0, 3. This one you'd have to go down 3. And then down 1. So its intercept would be 0, 5, which is bigger than this one. And this one's at 0, 3. So it looks like this one has the star next to it. I didn't see that was two different ones, but yeah, so these are two different problems. Hold on a sec. Dang it. My iPad was covering up the 10, so I thought it was all one problem. All right, well, that's okay. I mean, it doesn't change anything. 9 still has the greatest rate of change, so we'll circle that. The star goes next to the table on number 9. On 10, the graph still has the greatest rate of change, but the greatest y-intercept on these is the table still. Yeah, on number 10, the 2 points should have had been circled because it has the least negative, so it is the most of the rate of change. The highest rate of change then. Yes. So there's only 3 things you need to know about linear and nonlinear. The first way, let's look at an equation, all right? An equation.
Wait, for when.
No, you wait. I'm in the middle of something, okay?
Exactly.
So the equation. An equation is linear if you have something like y equals x or y equals some kind of number. Now it can be in the form of y equals mx plus b as well. Just notice on these that there's the exponent for x, we don't see it, and the x is not in any kind of denominator. As long as that happens, it'll be linear. Nonlinear ones will look like something like y equals x squared, y equals 1 over x, y equals x to the power of 1/5, maybe a fractional exponent. Once we get exponents like that, then we get nonlinear functions. So that's equations.
Simple enough.
That's all we need to know about the tables. Linearity will give us a constant rate of change. The graphs, those ones are pretty easy because
You just look at it.
we're just looking at it, really. Yeah, that's it. So when we look at a graph, right, like these, would that be linear? No, because it's not a straight line, right? Well, what about these? Linear?
Yes.
Yes.
Sure. What about these?
Yes.
Yeah, that's straight. This?
No.
This one?
Yes.
What if it was just a point?
Yeah.
Yes.
No, it's just a point.
Wait, but then what if
What
it's
about this
like-
one?
what
Would
if-
that be a point?
You just drew it.
Oh yeah, sorry, my bad.
Wait, no, but what if it's like one of those weird like.
What if it was this one? Yeah, that's a straight line. What about this one? Yeah, no, now it's this curved line, so there we go.
Take a picture, someone take a picture.
Why?
If this resembles the likeness of anyone, it was purely coincidental. It is not based on any
Spencer, take
real
That
events.
reminds me of some kind of